designing of high power DC-DC converter, and there are different switching devices. Okay, driver
Hello, sir.
discussing over here. So Riju, please start your session.
Okay. Good morning, everyone. Sir, am I audible, sir?
Yes, you are audible.
Okay. Good
From the
morning, everyone.
participant name, please confirm. Is he audible?
Am I audible?
Yes, sir.
Okay. Thank you. So, good morning, everyone. My name is Riju Nandi. I am doing a PhD in NIT Rourkela under supervision of Dr. Arnav Ghosh and Dr. Krishna Roy, sir. So now I'm going to present that high power DC converter designing. So layout of the presentation is semicron IGBT module, that switch I have used for the designing purpose. Also A-shaped finned aluminum heatsink for the for the heating purpose, cooling purpose. Also I have used A-shaped finned aluminum heatsink. Sorry. So then third is inductor. So I have designed the inductor that current rating is more than for 20 ampere. Capacitor, then semicron gate driver board and protection circuit that protect the IGBT module and for the drive that IGBT module. Also TLP250 driver circuit, and third is snubber circuit for the protection of switch. Then uh, I will show the design of the bidirectional buck-boost converter that I have designed in lab. So this is the semicron IGBT module. You can see that what is IGBT module? That IGBT module means insulated gate bipolar transistor module is a semiconductor power switch. This is a semiconductor power switch that combines the high input impedance of a MOSFET, easy gate drive, and a high current and voltage handling capability of a BJT. Both both are there in the IGBT module. So why it is used for a high power application? That high power systems such as inverter, motor drives, induction heating, UPS system, and renewable energy converter like a buck boost, any converter need efficient, reliable, and compact switches. So IGBT module are ideal for this because they offer high voltage and current rating. That I have used that IGBT module. That module can handle 1200 volt, means 1200 volt and 100 ampere. Okay, means 12 kilowatt like total. So perfect for industrial motor, EV traction inverters and solar inverters. Also for the microgrid also. So you can see that it ranges up to 1200 volt and current rating 100 ampere. That's why I have used that switches for the high power application. Then you go for second is low conduction and switching losses. So IGBT has a low voltage drop in the on state. So in on state that IGBT voltage drop is very low. So that's why also that's why this is the low conduction mode. Also switching also for fast switching. That switch is very fast. Means fast switching timing is very fast. So which means high efficiency. So that output I will get, that is a percentage of is very less. That's why now it is a higher efficiency. So easy to control, that the gate is the voltage control like a MOSFET. No large current is required. So that the gate to source voltage is a like a MOSFET. No large current is required. So little bit current also it will trigger. So integrated packaging. So module like this one contain multiple IGBTs. Means you can see there is a two IGBTs there in the module. You can see that two IGBT module is there. Okay, so that is module like one contain multiple IGBT and fueling diode in one thermally efficient housing. So many IGBT modules there's three IGBTs there, four IGBTs there. So in I have used this semicron IGBT module. There is only two IGBT switches is there and freewheeling two freewheeling diode in one thermally efficient housing. So simply simplifies assembly, cooling and electrical correction. So this is ruggedness and reliability that they include isolation and are designed to handle surge current. So in IGBT module they include isolation also. Okay, and are designed to handle surge current means when current is little bit high, that kind also it can handle that over voltage. I already told that 1000 up to 1200 volt it can handle. So this is over voltage and thermal cycling. So how it works, then structure. Structure means each IGBT has three terminal. All know about it: gate, collector, and emitter. Okay. So operation is when the positive voltage means 15 volt is applied between the gate and the emitter, the IGBT turns on, allowing the current flow to collector to emitter. And when the gate voltage is zero or negative, it turns off, blocking current flow. Okay. So internal diodes means the schematic symbol printed on the module shows anti-parallel diodes across each IGBT. You can see that two IGBT in anti-parallel combination. So the symmetry symbol printed on module shows anti-parallel diodes each IGBT. So this fueling diode allow current to flow during switching transition in AC or motor drive circuit. So typical configuration modules often contain two IGBT arranged as a half bridge. So that modules I have used for the high power DC converter designing. So two IGBT arranged as a half bridge. You can see it is it is a design as a half bridge. Two switches are there as a half bridge. So this allows easy implementation of inverter circuit converting DC to AC. So this is the IGBT module. Then I'll go further for A-shaped fin aluminum heatsink. You can see this is the heatsink for the that heating purpose. Okay, that for cool the IGBT, the cooling for the IGBT to protection the IGBT. Okay, so why used for the high power application? The high power devices handle large current and voltages. So that I have designed that microgrid for the up to 20 ampere current. So we have to handle this current and voltages also. Voltage like than 400 volt, uh, 400 voltage. So which lead to greater power losses, I score and switching losses. So the generated heat must be removed efficiently to keep the junction temperature within safe limits, usually below 150 degrees centigrade. So when temperature is high, that heat must be removed. So that heat sink uses for that remove that heat. So the bigger surface area and material properties of a heat sink help improve thermal conduction. So for reduce the heating reduce the heat. That's why improve thermal conduction. Also enhance nature and force convection. Allow high power dissipation safely. So next is inductor. This is a for the high power application inductor. So this inductor we have designed in workshop. Okay. So in our lab also we are using that inductor that I have designed. We have designed this inductor. So why this is a high power inductor? That that for the inductor I have used 8040 core, E8040 core. Okay, this is the ferrite core is there. Also, you can see the middle portion. There is a thick copper. Means there is thick copper or is there for rounding. Thick copper is there. So this is 12 SWG. Thick copper is there for handling the current for up to 25 ampere. Okay, this is a proper that upper portion you can see that a proper insulation is there. That coil wrapped is there. This for higher temperature insulation tape. Okay. Okay, so in that between the core, you can see that there is a air gap is there. So depends on air gap, you have to measure the inductance value. So when that if you want inductor value is high, that you can go for go for that paper insulation thick. Okay, that you have to increase the air gap also. Okay, like that. So why this is hyper application inductor? So I have said that the large core size means ferrite core EE8040. So the big square magnetic core can handle high magnetic flux without saturating. Sorry. So this is a high magnetic flux. This can handle without saturation. This allows it to store more magnetic energy and carry higher current. Am I audible?
Yes, you are audible.
Yes, sir. Yes, sir. You audible. Yes, sir.
Sir, this
Yeah,
gap,
carry
air
on.
gap, should be very large or very should be very small. A small.
No, it depends on your inductor value. You can when you want the inductor value is large, inductor value is, you want inductor value is large. That's why you put some paper for this. Like you have to increase that air gap also between that inductor, this inductor between the inductor. So when you want a low voltage inductance, you can change. That's you can change. You have to put some wire, not wire paper for this. So you can change how much you want that inductor value. Means change it. Suppose you want 1 millihenry like that, but you have made 1 millihenry, but you want to 1.2 millihenry. That time you should increase that paper size also. That gap. Okay. So
So another aspect is if that gap is increased, we say some like leakage, flux, and all. We say no, that will not happen, or what is that? Please correct me.
that leakage is there, but that time also inductor value also increase, but that not won't affect. And there's
Okay,
some
sir. Okay.
little gap means not more than some little means 2 or 3 and 4 paper you have to put something then that small thin paper. Okay, so this is the so this is the okay for carry higher current. Okay, that I have used for the that store the magnetic. So next is thick copper wires. This 12 SWG wire that you can use 16 SWG. Depends on your current. Okay, you have used that. How many current you want like that. So I have used 12 SWG wire, thick copper wires. So the inductor uses thick copper wires winding, often with insulation slabs. That insulation shapes is there. For the thick wires, reduce resistance and lowering copper losses and keeping it cool at high current. So I have used for like that 20 to 25 ampere. For this I have designed. So proper insulation, you can see that the coil is wrapped with high insulation tape, temperature tape. Okay, so when current is high, that time temperature also high. So that for the insulation, I have used that coil. Okay, insulation safety and reliability at high voltages and current. So the small visible gap between the magnetic core, sorry, indicates the air gap design. Okay, this prevents core saturation when high DC current flows, which is crucial in power converters. So like DC-DC converter or inverters. So next is capacitor. That capacitor I have used. Many capacitor is available in market. So but I have used this capacitor that I can company the capacitor. So why it is for high power application, like for high voltage rating, that you can use that high, this rating is 450 volt DC. So if your microgrid like about 400 volt 300 volt or 200 volt, you can use that 450 volt DC, because about means if it increase about 450 volt, so that time capacitor is damage. So this is a 450 volt DC. This capacitor can safely handle hundreds of volts. Okay, typically of DC bus or power supply filter circuit in the converter and inverters. This is a large capacitance value is you can see that 2200 microfarad. So why I have used that 2200 microfarad? Such as high values of allows it is stored large amount of energy, helping to smooth high current ripple, supply surge current during switching events, maintain stable DC voltage during load changes. So you know that capacitor we are using for capacitor for reduce the voltage ripple also. So and the stable the DC voltage means I have to we have designed the DC microgrid, so we have to stable the DC microgrid voltage. That's why we are using that large capacitance value in capacitance. So aluminum can construction this construction like can. Okay, this is aluminum can construction is there. The metal can provide excellent heat dissipation and mechanical robustness. Okay, essential in power circuit that experience high ripple current. So next is high ripple current capability. These capacitors are designed to tolerate large AC ripple current without overheating. And a key recommend in power supplies and DC links and inverters. Where I have told about it that DC link means DC bus and for the power supply also that high ripple current capability for I have used but we have used for the this capacitor.
Sir, sorry, sir.
Uh-huh.
Sir, this type of capacitor can be used for snubber circuit and protection circuits?
No, snubber snubbers capacitors are different. For the switch protection, you have to use the snubber circuit, snubber capacitor. That I'll show the snubber capacitor we have used also. I will show. Okay. Hmm. So this is a semicron gate driver board and protection circuit. That is the gate driver board also there, but also protection circuit means you have to this circuit protect the IGBT module because you are using IGBT module. That IGBT module you have to protect because that IGBT module price is very high because very high means not compared to uh, simple IGBT. Okay. So you have to protect that IGBT. So that I'm using that semicron gate driver board and protection circuit. You can see that what is it that is mounted on PCB printed circuit board that contains that isolation and gate driver circuit is there. There is a isolation is there that also gate driver circuit also there. There is a optocoupler and or transformer for signal isolation is there. Okay, there's a protection circuit is there. There is a desaturation under voltage lockout. A connector for control signals PWM. This is the connector or for control signal for the PWM and power supply. So that you can see that is a pin is there after supply so after gate driver board you have to supply there. Okay, so that generate the PWM. Okay, and also protection is there. Okay. So that is passive component is the resistor, capacitor, diodes for tuning and filtering. So there is also passive components there resistor. You can see capacitor. You can see also diode also there for the tuning and filtering. Yeah, it can be tune and filtering also. But this is the I have bought means we have bought from the Semicron company that for the protection of the
Sir,
IGBT.
suppose it's a
Hmm.
tuning circuit you can use, then what is the resonance here?
Resonance
Resonance condition.
that I don't know because that Semicron company has provided this all the circuit, but for the switch protection, IGBT model protection. So though that's why we have used that protection circuit because there is a more connection in the Semicron gate driver board and protection circuit. Many means means protection also, tuning also, all there. But we don't know about what they design in the semicron gate driver circuit and within that we have design in KiCad also, but that for semicron I can't, because that semicron company have designed this part. Okay. So this is the 12V250 driver circuit. So I have designed the driver circuit in PCB in our lab for the drive the switch. So TLV250, what is the TLV250? This is a 12V250 driver, is an optically isolated gate driver IC made by Toshiba. Toshiba, that company, that IC, they made this. Okay, so it designed to drive the gate of IGBT or power MOSFET and using PWM signal from a microcontroller. So you can see there is a microcontroller signal you have to give, and there is a that output is coming from this side. Okay, and go to switch, get to source, get to source. Okay, in MOSFET by IGBT. So using PWM signal while maintaining electrical isolation between control and power side. Okay, this the TLV250 used for the isolation purpose also between the control, the microcontroller, also power side also. That's why we have used TLV250 driver circuit, because it can isolate. Why TLV250 used for converter hardware? Electrical isolation. The input, already I said, the input control side and the output, this is the output side. Okay, side are galvanically isolated by an optocoupler inside the TLV250. Also gate driver application amplification. The logic PWM signal from the controller usually 3.3 or 5 volt for suppose because if you are using microcontroller, suppose C2000, that time you have to give 3.3 volt, because that voltage it will come 3.3 volt. Or if you use an Arduino, anything, Arduino Uno, Arduino Mega at megas, that time it will give 5 voltage, near about 5 voltage. So it is not strong enough to switch IGBT. That voltage will come, that not strong enough to switch the IGBT or MOSFET directly. So the TLV250 amplifies this signal and provides plus minus 15 volt gate drive. Typically 15 volt for the turn off and 0 or minus 15 volt for turn off. Okay, sorry. There is a noise immunity and reliability. The power converters generate high DVDT and EMI noise. You know that EMI, electromagnetic interference, is there, when a high DVDT also there. So the optical isolation in TLV250 prevent these noise spikes from corrupting control signal. That isolation, the TLV250 prevents that noise. That noise is coming. That spike is corrupting covalent signal. That then is fast switching. That speed typical propagation delay is 500 nanosecond. That makes it switchable for medium frequency switching, like up to 20 to 30 kilos, because we are using IGBT. So we have supplied that to near about 15 kilowatts. If you using MOSFET, that time we are using 25 to 30 kilowatts, like that. Okay. So I have the 20 to 30 kilos for IGBT and 40 to 50 kilos for MOSFET also. But you can use also for IGBT 50 kilohertz, 15 kilohertz, and MOSFET also for 30 kilohertz, like the 30 to 35 kilohertz. It is also compact and low cost, because we have made in our lab also. It price is very low and compact also. That you told that snubber capacitor. The snubber capacitor we have used. Why? What is the snubber capacitor? The snubber capacitor is a high current and low inductance capacitor. So connected across the switching device. That I have told that in IGBT and MOSFET, for the protection of the IGBT and MOSFET, we have used the snubber capacitor. Or between the DC bus terminal you can use also. So to observe voltage spike and damp oscillation during switching. So why is snubber capacitor used for IGBT protection? that absorb the energy from this transient means L into di by dt. Also limit the voltage rise. That when the voltage rise very large, that time it limit the voltage rise across the IGBT. So it won't damage, so that voltage won't damage the IGBT also. Reduce switching losses and EMI noise. You know that EMI is the main part for the if you are using converter, because electromagnetic interference is there, so their losses is there, so that you have to reduce that EMI. So that's why you are using snubber capacitors also for reduce switching losses and EMI noise. Improve system reliability and extend IGBT lifetime. So so to, to extend the IGBT lifetime, we have used the snubber capacitor. Okay. Now you can see that whole the design part, that this is the bidirectional buck boost. So this is a boosting part, this is a buck part. Okay. So you can use that inductor value. We have used 2.3 millihenry. Core is EE8040. I have told all. Copper wires for inductor 12 SWG. A capacitor, two capacitor also there for the bidirectional buck boost. So there is a 2200 microfarad and 450 volt DC. A switch, I have been told that semicron IGBT module, and switch protection also there, and bladder resistance also there. So for the discharge, that capacitor also, capacitor capacitor value. Capacitor means when capacitor is charging, okay, that time you have to discharge. So we have to I have used the bladder resistance also, that is 5 watt 22 kilo ohm. So this is driver circuit, then is driver circuit, then is snubber capacitor. Snubber capacitor, I have told the snubber capacitor. So you can see that I have made the bidirectional buck-boost converter. You can see that this IGBT module is there. Okay. So this is IGBT module, that IGBT module, there is snubber capacitor is there for the protection the IGBT. Okay. So there is an inductor also there that we have designed, and so in workshop we have designed. There is a 2.3 millihenry. This is IGBT module. This is snubber capacitor. This is the protection circuit. Okay. This is the back side. Okay. So this is the front side. You can see that this is a sorry. This is the front side. You can see. The two capacitors there, 200 microfarad, 450 volt capacitor is there. This is the bladder resistance. You can see there is the bladder resistance is there. Sorry. This is the bladder resistance is there. You can see that 5 watt 22 kilo ohm is bladder resistance to discharge the charging of capacitors. This is a driver circuit is there. Okay. So I have designed the bidirectional buck-boost converter, that I maximum current is 15 ampere and voltage maximum is 200 volt, that it can handle. Okay. So so power, it will like the 3 kilowatt, it can handle up to 3 kilowatt to 3.5 kilowatt. It can handle for any switching frequency. I have told that 15 kilohertz frequency. So this is this is the designing portion. Okay. So next, any question about it? Then I will go further
Yes,
for the
sir.
alter.
Yes, sir.
Okay.
Hello.
Yes, sir.
Sir, this RGBT model is available in the market, no? This
Yes,
brand.
available in market also. You can go in online also. Online robo company also there. Any company also there. Yeah, system company is there. Any company is there.
Okay. Robocop.
Company
Okay.
in online also there. In offline also you can go.
Okay. Okay. Thank you.
Hi, sir. This is Bhuvan.
Hmm?
Sir, I have
Right.
one doubt.
Actually, we want to supply negative supply voltage to turn off the IGBT or no need, sir. That one.
Which part is this?
I'm
This part.
asking. I'm asking in TLP 250, sir.
Okay, okay. 15 voltage for turn up. Hi, you for turn up. No,
That means
you
for
can't. Yeah,
yeah.
don't use.
Actually,
You
for
can.
example, we are giving the positive 15 voltage to turn off the IGBT or MOSFET. Similarly, we want to turn off the IGBT to fast means either we want to supply negative 15 voltage or no need, sir. That one.
But negative no. But when you're using IGBT module, na, that time -7 voltage is the uh, -7 voltage. You have to turn off the -7 voltage. Uh, that IGBT module plus 15 to that -7 voltage. Okay, that
Mm.
that time we have to give -7 voltage to turn off, because that both switches in anti-parallel. Okay,
Yeah,
so
yes, sir.
suppose you are using for using for half bridge, so you have to turn off one switch, then it will go for another switch. Okay, so that time you have to give the -7 voltage, okay, to turn off that switch. Okay, that time, so that time you have to use some voltage shifter also. Okay,
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 sir.
that time you have to some voltage shifter to turn off the switches, because again because if both are turned on in same time, the switch will damage
Short circuit. Yeah, yes, sir.
short circuit. That's why you have to use some voltage shifter. Okay, for the
Yes.
uh, for this part. Okay.
Sir, I have another one doubt also, sir.
Mm-hmm.
Can I ask, sir?
Yes, yes, yes.
Sir, actually, what is the optimized value for the gate driver resistance? Actually, we are using by either choosing the resistor trial and error basis. Is there any particular design value to choose a gate drive resistance?
That TLP250 driver circuit.
Yeah, exactly. I'm asking that only, sir. Actually, from
Oh, but
60 pin,
no, you can see that it's available, that TLP250 driver circuits available in Google also. Okay.
yeah, yes, sir. I saw actually they are prescribing that 8 ohms, or sometimes they are saying 10 ohms, and then again they are saying 22 ohms in data sheet itself. And then when we are going for some IGBT data sheets, they are prescribing some values. When we are using that one, sometimes the ringing is causing in that circuit.
Acha.
So is there any
No,
exact
no,
formula to?
ringing. Because of you have to. Acha, you have designed the PCB in your lab.
Yeah, yes, sir.
No, you have designed. So ringing loss for the, you have to put a whole, means not part, up to that part you have to hold that IGBT module. But if you increase that leg, if you increase the leg when you do soldering, na, that time ringing part will come. Okay.
Oh, okay.
That-
Uh,
okay, means because you have to put all the things, okay, in PCB, and then soldering, means
okay.
up to this. If you if you if you go for suppose your PCB leg is big, larger, then
Hmm.
you have shoulder. Suppose you shoulder this thing, that time ringing will come, ringing frequency will also come. Okay,
Okay,
that
sir. Okay, sir.
you have to check.
Okay,
Okay.
sir. Okay, sir. Thank you, sir.
Okay. So next, I'll go for controller design of bidirectional buck-boost converter. That's why I have shown the bidirectional
Sir,
buck-boost converter. Yeah, yes.
sir, regarding one question regarding that driver circuit, sir.
Yes.
Sir, if you increase the frequency, maximum frequency, if you increase the driver circuit means whether we will get the correct output, sir. Because I want to know increasing the frequency of the driver circuit, we'll get the output in best way. So maximum, how much
Maximum, not maximum,
we
but
can
because
increase it?
if you're using IGBT, na,
Uh,
that I have used that IGBT, it won't handle like 50 kilohertz to 100 kilohertz. Okay, because you have to give from that microcontroller. Suppose C2000 Arduino, you have to give that
Okay.
frequency range. Okay, suppose I have give 15 kilowatts, 15 kilowatts. That output also going from 15 kilowatts and go to gate means switches, gate to source, anything. Okay, MOSFET, IGBT4. Okay, so you have to give that in microcontroller how much you want. Okay, means 20 kilowatts, 25 kilowatts. That IGBT can't handle 100 kilowatts. That if I put that 100 kilowatts in the microcontroller, it can damage the IGBT module.
This
So
driver circuit is used with SiC carbide and gallium also. It will be useful because now the recent research is going on silicon carbide and gallium. Whether this TLP250 driver circuit can be used for that also, sir, or any other specification will be there, or any other configuration will be there.
no, it can also any IGBT or MOSFET also.
Hello, sir.
Hello.
Please, please,
Actually,
sir.
yes, for gallium nitride or SiC, I think driver will be different. Okay, because their logic is different. Okay, in this driver circuit,
that's
we
why I
are
want.
basically, you can see the TLP, and suppose you are using TLP 250 or TLP 350. Sometimes we are also using MCT. So based on their ability to handle switching frequency. Okay, it's not about that whatever microcontroller or whatever DSP processor you have to generate the pulses. But thing is that the optoisolator or the driver chip we are using that is able to handle that amount of frequency or not. Okay, and that in our case we have observed that our converters are running good approximately in between, I think 20 kilohertz. Okay, 15 to 20 kilohertz. Okay, we are operated the operation. Yes, that's why also our target is that to get the high power application. Okay, so if we increase the power level, the switching frequency going to be less most of the cases. But right now, lot of devices are there. They can also handle good high frequency as well as moderate power range also. Okay, so in this case, you can see the driver circuit range maximum 20 kilowatt, not more than that. Okay, for our dedicated application. Okay, sir.
Thank you, sir. Thank you.
Okay. Thank you. Riju, please carry on.
Okay, so now I'll continue about controller designing of bidirectional buck-boost converter. So that I have used in a simulation also, that I will show that study design 5 kilowatt wind energy system with battery storage and bidirectional converter. So the key challenge is maintain constant DC link voltage under wind speed variation also. So the battery is used to stabilize DC voltage during standalone operation. Okay, so the P&O algorithm used for MPPT control for the wind system, that PMEG system, and PID controller is implemented. I have designed the PID controller for the DC bus voltage. You have to stable that DC bus voltage, that I'll show. Okay. So that you can see that this is the wind PMEG system with battery. A small signal modeling of the BDC that I will discuss about it. So you can see this a wind turbine is there. So this is the rectifier also there. After PMSG, you have to use the rectifier. That this is a boost converter I have used for the maximum power tracking. Then is the DC bus. You can see that positive and negative. That power it will go to positive and negative DC bus. So you can see this is the bidirectional buck-boost converter. So this is the battery. Battery is there. When battery is this battery I have used for 144 volt, and our DC bus voltage we have maintained that I have maintained then 350 volt. When battery want to charge, that time 350 volt going to that charging that battery. Okay, that time BDC behave like a buck converter. Okay, when battery is fully charged, that time when DC bus voltage is required, means voltage is required, that time battery will discharge the that DC bus voltage that time BDC act like a boost converter. Okay, this is DC bus. This is a load. This is the simple R load. Okay, this is the R load. This is the capacitor is there. Just stable the output voltage and the discharge voltage. This is the load is there. Okay, we can see that the linked Win PMSG system using a BTC with storage system. This is a storage system, is you can see a boost converter and a rectifier full bridge. I told already that this is the rectifier, and the wind turbine PMSG make up the system that rises the DC bus voltage. One can modify the duty and obtain the system peak power using P and MPPT algorithm. That we have to. I have used that P and MPPT technique for the tracking for the MPPT of the PMSG. So which manage the MPPT energy from wind turbines and PMSG system and the parallel connected batteries would power a BTC and converter controlled by PID. So that you can see that I'll control that voltage that we using PID controller. So you can see that this is the BTC, means a bidirectional buck-boost converter. In
Sir.
short is BTC converter.
Sir,
Yeah.
you have connected externally this capacitor across the
Yes.
load, or it
Yes.
was inbuilt?
No, it is inbuilt. Inbuilt means in converter inbuilt.
No,
Converter.
this one CDC is the capacitor, and you have used dynamic load, no? As a load
Yes,
means
yes.
it was shown. So this CDC is externally connected or what?
This is externally connected in the simulation, but in hardware I have not done externally connected.
Yeah.
Okay.
Okay.
Okay. For the bidirectional buck-boost converter, you can see this is a bidirectional buck-boost converter configuration. There is a parasitic resistance also there. So low that parasitic resistance also there. So that the growing popularity of renewable energy sources in electric vehicles increase the demand of bidirectional power flow converters. So for the buck and boost using, okay, voltage and current regulation transfer function are derived from a unified buck-boost converter model. So that a voltage transfer function in current transfer function you have to use for the controlling. So you have to derive that transfer function. So that I have to told that the input voltage means battery voltage I have used for 144 volt. Okay, and output voltage means that 340 near about 350 volt for the bus voltage. Inductor 16.2 millihenry. Input capacitor is 1 millifarad. That you can see that 1 millifarad I have used, and output capacitor is 15 millifarad. Okay, that output, and input internal source means that RP. You can see that in RP is there. That this value is very less, means 0.55 ohm. And input capacitor ESR, you can see that ESR is there. RCI is there. Is the value is 0.074 ohm, and output capacitor that RCO I have used for 0.005 ohm. That DCR of the inductor, you can see that DCR is there, that is 0. Very negligible, means 0.0096, near about 0 also. And load resistance I have that for the simulation done for R load is 26.7. Okay, the load for 26.7 I have used for load, and time period is 50 microsecond. That it will convert into frequency also. So you can see that this is the small signal modeling of BTC and battery charging and discharging with bidirectional buck-boost converter. So you can see that the model can be developed using state space averaging method. So that V0 by D equation I have made from using small signal modeling. So you can use also state space averaging model. Both technique you can use. So to derive the transfer function between duty cycle and output voltage V0 by D. So used in control designing, some voltage mode control, current mode control. You can use for anything. Means I have now I have used for voltage mode control. So current mode control you can use also. Help analyze dynamic response and stability of the converter. So because you have to stable the converter in the closed loop. So so that time you have to figure out about what is the V0 by D equation, then you will go further. So you can see this is the V0 by D equation I got, that D S plus G S plus R dash by L E plus F, the S plus G. What is the D? D, you can see that minus I0 means output current by 1 minus D C0. Okay, C0 means output capacitor, that you can see that. What is the E value? Rp square by LCI Rp plus RCI square. Okay, what is the F? F value, what is the F? 1 minus D duty ratio minus C output capacitance, and Vp means input voltage. Okay, 1 minus D minus I0 Rp plus RL, 1 minus D square. And what is the G? G means 1 by Ci Rp plus Rc1. And what is the H? H is the R dash by LCI plus Rp plus Rc1. What is the I? You can see that it is a big equation, so that's why I change all the things like that. So I, what is I? I 1 minus D square LC0 Ci Rp plus Rci. What is the R dash? R dash RL means that inductor resistance. So DSR also, you can see that DSR is DCR, sorry, DCR is there. So 1 minus D RC0 plus RCI RP by RCI plus RP. So this is the small signal model. Uh, I have done this equation. Okay. So now we go for further for PID controller. So the proposed PID control begins by identifying the required negligible operating point for bidirectional DC-DC converter. It adjusts the BDC to maintain operating near this stable operating point, even in the presence of noise and set point changes and unexpected disturbance. If set points also change, but disturbance will come, it will control the DC bus. Okay. So the PID controller regulates the BDC converter switching device by generating the corresponding PWM pulses. Okay, so you can see this is a structure. Okay, that reference voltage is coming. Or if it is the reference voltage I have used, that output that voltage is there, that output voltage is there, YS. That going for error will come. That this is a PID controller. This is a controller part. You have to control that the things. This is a plant transfer function. This is a plant is there, GS. So this is a general structure of PID controller. When Kp equals to proportional gain, Ki is, you know, the internal gain, then Kd is the derivative gain. So for my simulation in CC tool, you will see that for the PID controller, the transfer function I have used that 0.00578 plus that the pole is S and means 0 pole and is a minus 60.2. Okay, and 0 also minus 77, 9.5 and 35. That equation is transfer function of the PID controller of the BTC. So now I'll go for the simulation part for the controlling. So I already told that that what is the input voltage, or the RP, what is the CCI or the RCI, that I'll do. I have done in coding part in the MATLAB. So you can see that first is S equals to transfer function S. Then VP, you can change also VP. It's all about your battery voltage. You can go for 24 volt, 36 volt, 48 volt, anything. But I have used for 144 volt, means 12 battery is there. So input resistance also there, that RP, 2.75, that I have told already. And that I have told already that RP, what is the RP? 0.55 ohm, already I have told. So this is the 0.5 ohm, like that. So CCI also, that RCI also there, that RL also there, L is there, C0 is there. That what is the output capacitor? You have to choose, not choose, you have choose anything. So inductor value, RCO value. That I have told that that in simulation that output current is 13 ampere, and duty cycle like that 0.59. So that is the coding part that reference as R1 plus 1 minus D into RC0 plus RCI into RP divided by RC1 RCI plus RP. So that is the designing SI simulation part, that A0. That coding part I have done, that 1 minus D by C0, that S plus 1 by CCI plus RP plus RCI. This is the formula based, and I have designed all the coding part. You can see that because we have to because I have to show that what is the value of the V0 by D value after doing the coding, because also you can done also in paper also you can do that, what is the after using small signal modeling and circuit averaging technique, you can do also that what is the V0 by D equation. Okay, but I have done the coding part in MATLAB. So this is a C2 value of C1 10 RC0, that C is 10 R minus D and RC0, that I0 is I0 by 1 minus D is the formula. I know the boost formula is there, also Buck formula also there. That formula you have to choose. There was a BCI value for buck boost, BC0, that is the formula you have to give. So this is you know that the output voltage by IL, you know that IL means the inductor current. This formula is MIN, mean real YIL. Then ZPK means zero pole that value, that YIL, that YIP also means output voltage, input current also. MIN mean real YIP, then ZPO IP. Okay. So the last part is, you can see that Y into V0. This is a V0 by D. Okay, that the V0 by D mean real Y V0 and Z Y V0. Okay, hold on. That Bode is also the Bode plot. You can see that Bode plot. You have to do it. So that legend, that you can see the title comparison of defined transfer function. You can see that legend is I1 by D, IP by D, V0 by D. But for the contouring the transfer function, you have to design mainly V0 by D. Okay, switching frequency 20 kilohertz. I have used for 20 kilohertz also for the simulation, and TS is also 1 by Fs. You know what is the timing 1 by Fs, that YIL. That is the coding part. Okay, after you see that after running this part, I can see that
Excuse me, you got all the poles located on the negative side of S plane? Excuse me, sir.
yes. All the
So,
negative side, all the negative side. So
that's why pole placement is it not required. You got a controls, control,
no. For
stable
the
system you got.
stable system, na, for stable system you have to go for negative, means a negative pole side. For positive, this is the another not stable. When not when suppose pole is S minus something, so you have to go the positive part. That positive part, this is the unstable part. But when go for negative part, this is the stable part in the pole side, left hand
Yes,
side.
you got a stable system.
Hi, I've got the stable system.
Yeah, that's.
Okay. you can see that last part, this is the B0 by D equation. Okay, so I have got after the coding part. Okay, now you have to type CISO tool. Okay, CISO tool I have to write. You can see that I have write the CISO tool, then enter. Taking some time, 1 to 2 minutes. You can see the border plot has come that time. P0 by D. Okay, so you can see that you can see that that CC tool has come. Okay, so you have to go first is preference. What is the preference? Is 0 pole gain. Okay, so you have to select. If you have to go 0 part, and there is a style option is there. Also option is there. Okay, you can see that option is there. You have to click that 0 pole gain. Okay, the time constant nature frequency also there, but yeah, I have done this is 0 pole gain section because your gain is there, your pole is there, your 0 is there. That's why I have selected that 0 pole gain. Just apply and okay. Then you can go edit architecture. Okay, edit architecture. You can see different architecture is there. Different architecture is there. This and this and this. Okay, so for the PID controller, your architecture same like this. Okay, because for the PID, F is 1, C is there, controlling part is there, plant transfer function is G there. This is the feedback. Okay, so V0 by D is your plant transfer function. I have said already. So you have to select the G value. So you have to click the G value. Okay, that negative part. So you can see that at the last Y by V0 is there. Y by V means V0 by D is there. Okay, you have to select this Y by V0, then import and okay. You can see that all the shift response, body plot, root locus has come. Okay, so you have to tuning this CISO tool. Okay, you have to see you have to figure out that your what should you will it a low or high. Okay, you have to done in low overshoot, and rising time also so fast also you have to do it. So I already told that I have designed that CPID value is 0.00578 and pole is 2 pole and 2 0 is there. So one pole is 0, one pole is minus 60.2. Okay, so you can go for that control transfer function. You can go. So there is you have to choose add pole, real pole 1. Okay, another pole you have to add real pole. Okay, so that pole is 0. I have already told that one pole is 0, only S is there. So next part is second pole. Second pole, what is this second pole? I forgot that. Next pole is a minus 60.2. Okay, minus 60.2. Okay, so you can for real 0 part. That 2 0 is there, so you have to select 2 0. You can see that 1 0 is there, so 0 means 79.51, and second part is minus 35. Okay, and gain is 0.00578. You can go peak response, ice time, settling time, transient time, steady state time. Okay. So now you can see that overshoot is so high, so you have to change. Acha, that pole you have to change something. So this is 16.2. Sorry, not 16.2. Come, but pole L0. Sorry, 35. Oh, acha, okay. Now you can see that after the putting that value, okay, that control transfer function, that overshoot is near about 8%. Okay, you have to change also. You have to decrease also your overshoot also. Okay, also that is a transient time 0.0799, and this is the rise time 0.189. Okay, this is the steady state value 1. Final value is the 1. Because you have to because after the steady state, it is a steady state in the stable system. So you have to controlling this part. So after the controlling, I got this value. Okay, I got this value that that overshoot is minimum like the 8%. You can go further because you have to change something that gain value, some pole zero values you can change. It will go further like 5% also you can do, but I have done for 8.59%. I'm showing now. This is the rise time. This rise time you can see you can see that 0.0186, and this is the transient time. Okay, so now go for the one part is I have to do. Wait for 2 minutes. This is 79.5. Okay, then is go for S plus 35. This is and this is 60.2. Okay, 60.2. You can see. So you have to then go for cascade. We have, because plant transfer function and control transfer function, you have to cascade. So cas equals to G into C. Okay. There is a M is the feedback cascade version, -1 is the H feedback. Okay, this one is there, and this is a step response. You have to see the what is the step response after this. Okay, so after running, okay, we'll get that figure. Submit. Sorry. You can see that you can get. I have got that response also. Okay. Also, you can go for body also. Okay. Control R and body also. Control T. So after run, so you can see that I've got this body plot diagram also. You can see this the gain margin plot also. If you go for peak response, if you go for minimum stability margin, if you go for all stability margin, you can choose all the things. So what is the PCF or the GCF? You can see that the PCF is 75 point. Sorry, phase margin is 75.3. You can see. Okay, so also for the control R, control R, you can go for root locus also. Control R. So after run, you can see what is the root locus will come. Okay, so both fourth part I have covered this step, body and root locus and Nyquist plot. That you can see this is the root locus part. Okay, in the root locus part, you can see that it's the root locus pass. Then go further. This Nyquist plot, control R and control T. So after running, you can see that this is the Nyquist plot. I have covered. This is a Nyquist plot I have done. Okay, so this is a stable transfer function I have done. So this transfer function I'll put the simulation, and after running you will see that stable the output voltage. Okay, so you can see that is the simulation part. So you can see that you can see that wind turbine is there. Okay, that is the PMSG. Okay, PMSG is there. There's a rectifier also there. So that 5 kilowatt after the PMSG, the 5 kilowatt has come. Okay, so the 5 kilowatt put in the Bush converter. That Bush converter, then I got near about 4.5 kilowatt. So this is the MPPT technique I have used for the wind PMSG system. Okay, that, let's see. Also now beta is value 0, you can change beta value also. Suppose wind speed, you can vary the wind speed. Then now wind speed is 12 volt meter second. That is the, okay, this is a WR value and PM value also there. There's a 9 kilowatt is there. I have given that wind from the wind turbine. So there is a boost converter. There's a capacitor, input capacitor also there to stable the voltage. Then there is a boost converter. Okay. So this is the PV volt, and this is a P volt. A B volt means this is a DC bus voltage. Okay, this is a DC current output, or is a current output for the DC current, DC bus current. Okay, this is a P load bus. What is the power of the DC bus? So you can see that this is a bidirectional converter. I have modeled this. This is a bidirectional converter for the buck part and the boost part also there. Okay, for the charging and discharging. This is a battery. I have to click that battery. Okay, this is a lead acid battery. This is the normal voltage is 144 volt. I told about it that 144 volt I have designed. This is the rated capacity 42 ampere hour. Initial rate of charge depends on you when 80%. If you give for 50%, then SOC come near about is 50%. The battery response time 1. Okay. You can see that controlling part. That I have designed this controlling. Okay, that 5 voltage is reference. So suppose V voltage is 350, our voltage is 350. So gain is 1 by 70. So 1 by 70 means 5 voltage near our 5 voltage. So it compare this part, then it then error will come. That error you have to control. That can control part is PID control. That QID control I have designed this part 00578, and this is the S plus 79.5 that I have already done. Okay, then it will generate a DT ratio 0.37, suppose 0.4, 0.5, anything. So that is the relation operator is there. Okay, this is the relation operator there. So you have to compare the short tooth wave that 0.002 that I have. You can see that output value minus 0.5 to 1, and time value 0 to 0.002. Okay, you have compared, then it will generate the PWM for 0 to 1. Okay, so now I'll run this simulation. Okay, for not 7. Okay, 7. Make it 7. Okay, it take some time. Okay, after running, you can see. So it takes some time. So for simulation, because there's a 2-3 minutes it take times. Okay, that you can see that time is 0.004. It go further for 7 seconds. Okay, so wait for sometimes 2 minutes, 3 minutes.
Sir, meanwhile, can I ask a question?
Yes, you can question. You can.
Sir, actually, the model you have shown in starting, the PID model.
Okay.
Sir,
That
yeah. Sir, while developing that model, like how did you develop that model? Like it was a trial and error method, or like how did you, like what was the journey?
this is trial error method. Okay. That I have
Okay.
changed all the pole value, zero values, pole value, zero, that I have tried so far. Okay. Then I
Yeah.
got this value for then that is a minimum overshoot, rising time is less. You can go further also because you can change also pole zero values. Then gain value also depends on gain value. You can change the gain value 0. Now 0.0578. You can change 0.0678, 0.658, anything. That you have to go further. That it minimal overshoot and rise time also for rise means faster. Also settling time also faster.
So previous to it, there was one more model, the transfer function. Can you just show it, sir? Previous to this.
Previous to
Yeah, this one, sir. Yeah, 16 number.
16. Okay, this is the V0 by D equation. This after the small signal modeling for the Buck-Boost converter, okay, bidirectional Buck-Boost converter, I got this with the V0 by D equation.
So sir, can you tell me about this? Like, how did you, like, you have derived it, or it took like how much time, or how did you do that? Like the journey between behind this.
Okay, no, you can derive in the pen and paper also because
Okay.
if you know the circuit averaging technique or small signal model technique, you can do all the any converters you can do. Okay.
Okay.
Can do any converter because it just take some time. It take times for the mathematical part. Okay, circuit. If you do circuit averaging part, it takes a little bit time because circuit averaging is short, but small signal modeling is that part is bigger. Okay, you can do
Okay.
both. You can use both. Okay, any converter. If you're using buck converter, boost converter, Leo, anything. Okay, you have to do that equation V0 by D equation using small signal modeling and also circuit averaging technique. Yeah.
Sir, any literature or book to start with very simple circuit?
The book that book I'll tell about. Okay,
Maybe a
thinking.
paper.
Okay, okay, I'll tell that. That I wrote one book, but I forget the name. This is to that. Okay, I will tell. Okay, I'm thinking.
Sure,
Okay,
sure.
I'll tell. I'll tell.
Yes.
Sir,
Mhm.
if you want to
Tell.
derive, sir, if you want to know the controllability and the transfer function, then we need not to require go for small signal modeling. To only design the controller, we require small signal modeling, right? Or wrong? I'm wrong.
No. Fast any converter. Okay, if you know the if you know the plant transfer function means V0 by D equation. Oh, okay. Then you go further. Means for controller designing. If you don't know about the plant transfer function, you can't go. You have to put that equation that what is the V0 by D equation. Our means
Sir,
any converter.
yes, sir. Sir, we write KCL, KVL, we know the modes of operation, then we write it and we find ABCD matrix, right? Then from
Yes.
in the steady state, suppose, then we just check the controllability. If rank is equal to that n by n, what is rank is there matching, then we can say it is controllable. Then can we find transfer function from that ABCD? Small signal modeling is required or not?
Yes, small signal required because also for the circuit averaging
Can
technique
you
is
tell?
also there. Yes.
No.
Can I share, madam, my opinion?
Yes, sir.
That you are right. Okay, but what happened when we are working on that switching converters? Na? So all the switching converters are highly nonlinear. What kind of
Yes.
nonlinearity you can able to see? That is called switching nonlinearity. That means periodically on, off, on, off. So if we see their phase trajectory, so we will get that limit cycle. Okay.
Yes,
So
yes.
itself it look like a linear, but it's a non-linear system. So small signal modeling normally we are doing for linearizing the converter. Okay, for designing the classical converter. Basically, if you see here, we are going to showcasing the controller like PID controller. Sometimes we are also doing lead type controllers. Like that, we are doing based on the merits of the converter dynamics. Okay, so in these applications, if we go for the classical controller, so we need to get that plant transfer function. Now, plant transfer function is control, that means converter output to control input transfer function, like that. Okay, so from there, if we have the plant transfer function, so we can design the classical controller, means everything in the linear platform. Now, if you go for the non-linear controller designing, suppose sliding mode controller designing, bang bang controller designing, in that case, what happens? You need not to do all those state space modeling and all other things, because if you have the differential equations and if you have the state variables, directly we can design the sliding surface, or based on your requirement, which type of, suppose if you want to design other kind of robust controller, in that case I think small signal modeling not so much important. Okay, so here it has been done because of to getting or convert your nonlinear nonlinear plant transfer, sorry, nonlinear converter to linear plant transfer function of the converter. Then we can design the classical controller. This is the basic platform of the studies. Okay.
Yes, sir. Fine. Thank you. Thank you very much.
Yes, welcome.
Sir, it's very good, sir. Actually, you should make some session on this one because we require some kind of input like this. Sardab, sir, thank you very much.
Okay. Actually, we thought that we are having, basically this is very crash level studies. So we thought that okay, next time we can take some, because this time the workshop already scheduled as per that. So definitely next time we can consider one session only for the modeling of the converters and their controller designing, like that. We'll keep it on that. Okay.
Thank you, sir.
Yes,
Thank you.
sir. Designing
sir.
of
Thank you.
converter and hardware development, it will be very good workshop then.
Okay, definitely. We'll do that. In next year, we'll do that. In every year, we are doing, because we are having a very busy schedule. So we are trying every year conduct one workshop. So all can interact, because student also getting some of the platforms. They can share their knowledge. Also, we are getting a platform to enrich ourselves from our esteemed participant. If you see the participant profile, all are coming from very good institutes. Okay, so we are gathering their knowledge also, and we can upgrade ourselves. Okay, that is a very good platform. So that's the way we are trying. So definitely next year, when we are going to conduct another workshop, we will consider another session for the basic switching converter designing, modeling, and finally the experimental thing. Okay, implementation. Okay, thank you. Riju, please carry on.
So now you can see after the running the simulation that current I got that 13 ampere and load voltage is constant in 349, near about 350 volt. Okay, that 3 volt constant, and got the power of the bus voltage is near about 4.5 kilowatt, and voltage is 349, near about 350 volt. Okay, so you can see that what is the wait, that is running, because that simulation takes time. That's why. So you can see that after the controlling that duty ratio come 0.375 and generate the duty ratio also 0 to 1, 0, 1, 0, like that. So you can see that that DC bus voltage maintained in 350 volt. Okay, that is constant. Okay, also DC load current that near about 13 ampere. It now is steady state part. Okay, after the controlling, this is steady state part. Then this is DC load power is a 4.5 kilowatt. You can see that you have to stable the DC bus voltage when you are doing some hardware part. You have to stable the DC bus voltage. If you that DC bus voltage will change, that time that circularity current will flow, it will damage your also converter. Okay, so you have to stable that the DC bus voltage. You can see that DC bus voltage is constant in 350 volt. Okay, then you can see that this is the SOC part. You can see the charging discharging. You can see that when fast battery is discharging, then it will go for charging. Okay, in charging this go for the discharging. Okay, after some time you also go for charging. Okay, that time it will regulate like that. Okay, at 7 it will come. Okay, so so you can see that last part is this this is okay. That this is DC bus voltage. Okay, 350 volt, near about 350 volt. Okay, is showing or not, I don't know. So you can show that DC bus voltage, this is the 350 volt, near about 350 volt. Okay, as the current is 13 ampere and this DC load power is 4.5 kilowatt. And you can see that the SOC, state of charge, this is the discharging, charging and discharging also. So you can see that SOC is 50%. It depends on your simulation. If you go further, that if you go that battery part, you can see that the initial state charge is 80%. Now it will come for 80%. Okay, if you put 50%, SOC like about near about 50%. Okay, you can see now SOC is near about 80%. Okay, so I have completed my topic. Okay, then if any question, okay, then I'll continue, because after that my colleague means on PhD scholar will go further for the next topic, C2000. Okay, implementation of C2000. Okay, so any question on this?
I have one question, sir.
Yes.
Can you get KBK values with CISO tool?
No. KBK value in CISO tool you can't get KBK value. KBK value you have to measure what is the KI, KD, that KT, that value. In CISO tool you can get. CISO tool you have to design. You can design on the value. Hence you have to design the controller.
Actually, sir, can I ask? Okay, can I tell? Okay, so in CISO tool, normally what happen? We are going to design for several controllers. Okay, classical controllers. So all do not have that KPKI value. Okay, suppose what is the KPKI value? Basically, if we have that pole and zero location, and as per their gain, we can say like that. This is KP, this is KI, like that. Okay, and in CISO tool, you can see it's a very good tool. If you change the pole and zero location, you can easily understand what is the phase margin, what is your gain crossover frequency, as well as their percentage of overshoot, rise time. When we are going to design the closed loop controller design, okay, when we are going to design the closed loop controller with cascaded with the converter, the response time is very much important. Means we should keep concern about least rise time, least overshoot, and maximum phase margin. So that should be our target. So based on that, there is a visual interface in CISO tool. We can easily see if we change the pole and zero location. So we can easily see their phase margin, gain margin, all the parameters. Okay, but three key parameters that I am telling you: rise time, peak overshoot, steady state error, okay, and phase margin. These 3-4 parameters are very key parameter, and if we are getting the optimum value by changing the pole zero location, optimum value, so other parameter also giving you the good results. Okay, that is our main target from the CISO tool. Okay, otherwise there, if it is okay, otherwise then the next approach also be there. If you are having any subcomputing tool, you can say like that, you can use any of the subcomputing or meta heuristic algorithm to optimize the parameters. That also gives you the best response based on their convergence criteria, means least error. If you able to find out, it can also give you the good response by that way. Okay. Riju, carry
Thank
on.
you, sir. Thank you so much.
Okay, Riju, carry
Okay. Okay. So, any question?
Sir, actually, I want to ask one question.
Yes. Yes.
Can we have a scope of for an algorithm where we can think of a value of kp ki kd, like the algorithm itself gives the value of kp ki kd. So in that way also, can we go for it?
That KPKI value for this, but you have to design the transfer function. Then you go for
After designing transfer.
KPKI, sir, KPKI KD is only related to PID controller. Suppose if you want to design the lead lag controller, okay, by using subcomputing technique. So in that case, there is no KP, no KI, no KD. Okay, so it should be point like that. The gain, okay, it will be like that gain. Okay, so instead of KPKI KD, you can consider different gains, K1, K2, K3, like that. Okay, that will be better approach. Okay, and any kind of algorithm, it can be done, no issue.
Thank you, sir. Thank you.
Thank you. So, any question about it? Designing high power converter designing and contouring part. Okay, so we can go further because my colleague will go for the C2000 implementation. Okay, so thanks. So Moinak will handle these things. Okay, my colleague handle these things. Okay, Moinak can do.
I have a small question.
Okay. Question.
Yeah, why can't we use the discrete mode controllers here? What is the scope of it? Because the analog controllers happen to be, that S-domain controllers, what you are designing happen to be almost outdated, and mostly the recent controllers, microcontrollers and all, we can design the controllers in discrete domain. What is the scope of it?
So now I have designed all the classical controller, like that PID controller, any PID controller, 2D PID, any PID controller. So that other controller I will go further because I have done not anything. So I will implement. Okay, now I have not done anything like that controller, that discrete controller.
Actually, sir, that classical controllers are not outdated. First, let me clarify the points. When you are going for the implementation, okay, so when we are going to implementation, that you are telling that now a lot of processor downloads are coming. So when you are thinking in the product aspects, okay, now government having more thrust on the designing of the products. Okay, so implementation of classical controller is quite easier. Okay, because suppose you want to design one sliding mode controller. Okay, the sliding mode controller, you are controlling your converter or microkit by using sliding mode controller. But where are you implementing? What is the platform of the sliding mode controller? The platform is like that. We are using DSpace, we are using Opalati, we are using Typhoon Hill. That different platform we are using. Okay, but point is that what will be the cost of the product? Okay, Typhoon Hill itself whatever name I am taking just now, I am telling about them. Their cost is around 20 lakh. Suppose if you want to design a microkit for your household application, so you are not going to implement with those control platform. This is not cost effective. Am I right? Okay. So point is that how easily you are going to apply your ideas for the real time applications and you are getting the outcome, okay, and which is feasible enough to in the product aspects, okay. So in that case, complicated controllers are very good. If we are able to implement in these platform, then we can appreciate, okay, that will be very good in manner. But a lot of challenges are also be there to implement easily in this form. Means we are using TI launchpad, okay, that its cost is less than 6,000 rupees, okay, and we are talking about this space and H Typhoon or whatever things, their cost is 20 lakh rupees. Okay, there is a huge difference. Okay, now one question may come that what is the efficacy of that thing? Okay, how that 5,000 equipment, 5,000 launchpad is good or 20 lakh? Definitely that is better than the 20. But our purpose is to design the cost effective product. Okay, and that can serve our regulations like load regulation, line regulation, means whatever challenges we are facing, that can be handled on that. So classical controller right now is very easy to applicable. So that's why we are giving more trust on that right now, the classical controller. After that, if we are successfully operated or tested the system in our current scenario, then we can try for some complicated controllers in that basic cost effective microcontroller or DSP processor kit. Okay. So I hope you are getting my points. Am I right, sir?
Actually, sir, I have some more doubts because
Yes, tell me.
system one happened to be a wind system, and
Yes,
you're rectifying it and you're converting it to DC.
yes,
And the second system happened to be a battery.
yes.
So how you're matching the voltage profile, and both of them are connected in parallel to the grid.
No, when we are integrating, if you see our laboratory session today, also our laboratory session is there. We can show you how they are working. Battery, wind, solar, three things are there.
You're
Matching
deviating
means
my question. Whatever I think, if you can, yes, this is the PPT, whatever is shown. So how both of them are connected? I hope it is in parallel connection.
Yes,
right?
parallel connection.
okay,
Yeah.
okay. This is schematic block diagrammic representation. That's why it is look like that.
Whether it is integrated or it is parallel conversion.
This is
It's
integrated.
Integrated.
Today's laboratory session, you can see they also do the videography as well as they can show the real time. How is it working? They can showcase.
Okay, sir. I understood. If it is integrated, the current should be same, which will be flowing through the load through both the converters. Was the design considered this type of methodology or not?
Voltage will be same. Okay, you have to maintain the voltage same. Okay, that current can be change your power rating. Okay, when you want that power 2 kilowatt, that DC bus voltage means power will current will change that 1 to 10.
What do you mean by integrated? Is it a series connected system or like what type
No,
of
no,
system?
no. It is parallel connected. All the parallel connected and integrated.
Parallel
You are
connected.
having a different source, sir. You are having different source.
So because
That based on the rating, the converter also been designed, then they are connected in parallel. Okay, we are making the voltage potential same and we are integrate them. Okay, and load also connected to the bus. Now we are checking what is the load current and voltage. That we are keeping the same voltage level. Now if we increasing the load, so voltage level we are keeping fixed, but current level is going to be changed. Okay.
Okay, if that is the case, sir, what about the circulating current?
This is a good question. The circulating current problem also be there. So that's why we are making the same potential. First point I am pointing out that we are keeping it the same potential, then we are going for the integrations. Okay, so circulating current definitely will be there, but this is very less amount right now. Okay, so that can be handled. Okay.
In the controller design, how that circulating current was taken into consideration?
Now, in the current controller designing, we are focusing on that profiling, means DC-link voltage profiling. Okay, that load is varying, any changes in the load pattern, so the DC-link voltage will be affected. So our current target is to maintaining the DC-link voltage profile, but that is not experimentally validated till now. So that is simulation we have done, and experimentally validated, we are integrated the system and we can run it for 2 kilowatt system. Okay, that is tested. Okay, within I think couple of months, that can be. Now we have to enhance the capacity of the converter, because we are having a setup up to go 5 kilowatt. So for that, we have to change the converter. We have to enhance the converter power level. So heatsink we need to be changed. Okay, now we are giving thrust on that, how to stabilize the voltage level of the DC link, because the load is going to be changed, increasing and decreasing. So that is our now point of concern, that we are working on that. Okay,
So one more question I have. The converter one, whatever is being taken, the diode is towards the output side, where the ripple current may be more, right?
Please tell me, Riju, please answer. I am having on phone call.
Yes.
Yes. Voltage ripple will be more. That time we are using output capacitor to stable the output.
Different issue. Output capacitor is to stabilize the voltage, and here we have two parts. One is converter 1 and the other one is converter 2. And converter 1 ending with diode. If you just
but in the simulation, that block diagram I'm showing, but in the simulation or in the hardware, I have used that capacitor in output.
No, let me finish the question. The second part of the converter, you're using switch S2.
Yes.
So this second converter, what you're going to take, will be acting in, because it is a bidirectional converter, it will be acting in two modes, buck mode and boost mode.
Boost mode, yes.
Yes. As you already said, the circulating current was not being taken properly. That will try to pose some important questions.
Okay. When the voltage is same, suppose we are using PV panel, then wind system, then battery. Okay, suppose 3 systems is there in parallel. That time we have to maintain all the voltage, output voltage is suppose 100 voltage. Okay, so we have to maintain near about 100 voltage same. Okay, so if voltage is like now some converter output voltage suppose 80 volt. Okay, some converter voltage outputs like output voltage is 100 volt. That time circuit current will flow. That time it can damage our converter also. But
because you're using a wind turbine system where you don't have a proper voltage and current profile, is it not?
Yes.
So how you're maintaining it? How you maintaining that constant voltage? These are some of the doubts.
Now we have done only open loop system. Okay, then open loop
we are using emulator now. That is a constant. Open loop system. Now we are using the emulators. Okay, so right now it gives us the constant voltage. Okay, for the generation part.
Okay, sir. Sir, my question is the last one maybe. When you're using analog controllers,
it's not analog controller, sir. We are not using analog controller.
Continuous controllers otherwise, whatever you're using in S domain. So how will you address all these issues?
No, not a S domain. When we are using
Riju, let me answer on that. Issues basically we are having when we are designing the controllers and the system. There are 4 or 3 key points. First thing is the regulations. Okay, so we are trying to stabilize the voltage regulations. Okay, of the DC link voltage. Yes.
No, I'm saying, sir, 2 regulations will be there. One is output voltage regulation. We know to D what you
input voltage. Yes, another one is the input voltage regulation. Yes.
Input current regulation or voltage regulation.
Because we are changing the voltage means definitely both will be power will be fixed, means both will be affected on that. Line voltage regulation, load voltage regulations, and that reference tracking. These 3-4 are the point of concern of us. Okay, now the system is running on open loop system. Okay, so when we are going for that closed loop system, working is going on. Okay, so I hope couple of months it will be completed. So voltage regulation we are maintaining first, then we can go for the input side. That energy management application, basically that portion is the next phase of work that we'll do after regulating the DC link voltage. Then you are talking about some points, na? So suppose input variations and all those things, then that point will come and we are addressing one by one. So when we are conducting the next program, I think that time all the work will be completed. That time we can showcasing in better way to, I think, you can also then give some good important input on that. So we can also modify based on that.
Yes, sir. Sir, I worked on this DC grids at IIT Delhi.
Okay. Okay, sir. Okay, sir. It's very good, sir.
So I know about this because he's a student. I'm just asking the question so that he can get a
Yes.
good insight of the circuits. That's all. Nothing
And
more than that.
definitely, sir. Actually,
Okay.
that's why
Thank you.
we are doing that interactive session that I am telling you now. We also learn lot of things. Okay, because when we are working in the real time system, lot of challenges are there. Because dealing with that 15 ampere, 20 ampere currents when it's going on with the setup. So definitely, you can understand. You are also doing the experimental work in very good extent. So high power application, we are going for that for standalone system. So we're getting good insight from our participants. That will be very good to us. Okay, sir.
Yes, sir. It's a good practice, sir, to get the students also to participate and involve and to present their topic so that they also come to understand and know. And we also will learn something and the other because the students are working. It's a nice
sir.
experience. Yeah, thank you. Thank you, sir.
That's why we are
Thank you, sir.
providing this platform. So they also learn something. We are
Yes,
also
sir.
learn something. That's a good
Yes.
thing. Okay, sir.
Thank you, sir. Thank you.
And
Thank
is
you,
there
sir. Thank you,
anything
sir.
else? So we can start the next session now, or is there any pending work is there in this section?
The
Sir,
session
I
is so
have
nice,
one
sir, and it's
doubt
very
about
clear.
it, sir.
I want to tell one. Okay, okay. continue.
Please tell me.
The session is so nice, sir, and so interactive. Many doubts has been clear. Thank you so much for the session. Thank you, sir.
Okay, thank you.
Okay,
Madam,
thank
you
you.
are telling something. One madam is telling something.
Sir, I had one small doubt, sir. In the
Yes, sir.
previous
Yes.
sessions, you had commented saying in the waveforms, output waveforms, it was shown that the power was varying according to the irradiation levels. And but in this session, here the power is being constant. Both power, voltage is regulated, simultaneously current is regulated, as well as the power, constant power you're getting it. But in the previous
No.
sessions, irradiation, based on the irradiation, the power was also varying and it became almost zero once irradiation was zero.
That this is no illness is there. This is I have used the
No,
wind
in the
system.
previous sessions for the solar,
Okay.
when you're
Okay,
using the solar, irradiation went when it went to zero, the power also was not constant. No, sir. The power was not, output power was not
That time,
constant. But in this
because
case,
that time,
power is constant.
yes,
How is
no,
that
no.
able to get?
That time, illness zero. That time, voltage kind also that time zero. That's why it's showing zero power. But there is I am using wind turbine. This is not a illness is there. So there's a PMSG. PMSG is there, which PMSG is there, permanent synchronous machine that generate 5 kilowatt system, then convert to boost converter, then it will give 4.5 kilowatt. This is the different part. This is a wind system are different. That PV are different. That's PV panel. So you can change. You have to change in wind system. You have to change all the speed value of the speed value of the wind. You have to change the speed value of wind. You can change all the speed value of 12 to 8, 8 to 5, 6, 6 to 2 like 0. When 0 will come, that time also power will go to 0 like that.
Okay, sir. But in PV system, it is not possible to obtain a constant power.
Yes, constant power you can take, but that time you have to give constant irradiance and constant temperature also.
Okay, only then you get the constant power.
Constant power, yes.
Okay, thank you very much, sir.
Thank you. So session is over, I think. sir. So any question? Okay, so I'll wrap this session. Okay. So next
Okay,
session.
so next session, I think we are almost in 11. So our next expert, Professor Prabhat Kumar sir, will join very soon. So the pending portion we'll discuss on tomorrow. Tomorrow session tomorrow we are having another dedicated session. So that session, the pending portion will be discussed by the Moina. Okay. Hello.
Thank you, everyone.
Okay,
Hello.
okay, sir.
Hello.
Thank you, sir.
Okay.
Okay.
Thank you.
Okay. Thank you.
So we are having
you.
some 5 minutes break. Then we can start this next session.
Sir, Arnav, sir. I'm
Please tell me.
Sir, can I get the email of Jaideep sir?
You please
he told-
WhatsApp me. You please WhatsApp me. I'll share it.
Sir,
Don't worry.
Okay, sir. Sir, I send on message on the WhatsApp.
Okay. You
Okay.
WhatsApp
In
me
the
my
group.
personal area. So
Okay.
in the group you have a message. Achha, that's why I'm
Yes,
not able
yes.
to see. You WhatsApp me. This is my WhatsApp number. Okay. I am
Okay.
sharing his. No issue.
Okay. Okay. Thank you.
Okay. Welcome. So we can conclude our first session. Okay, so we are waiting for the next session. When Sir will join, another 5 minutes break, then we can start our next session. Okay. Thank you all.
Thank you, sir.